Hey there, calc folks, back here with what I hope is another Mathematica demo for you. I do want to try to do a few of these with you, if not in class, at least through some video tutorials that I'll share out there on my YouTube channel, folks, where you've stumbled or have found this video. And we've been talking vector valued functions this semester up to this point, right, for the first few weeks of this course, where I think you've beaten yourself up enough in that work. Certainly I want to show you some Mathematica skills and ways of maybe building some programs in Mathematica that might help you with some of the interpretation of these ideas, and then certainly with respect to calculation, right, and give you that here, folks. This might help you with some of those thinker problems that you're focused on, or even come test day. I'm setting this out there right at the cusp of the test. You may or may not get to watch this in time, and my intent is not to be you using too much Mathematica on the test, right? But certainly after the test, you will have this demo to be able to go back to and help, and then certainly be able to work with in terms of getting done with your thinkers, right, for this test number one. Those few problems I gave you that are a little bit more of a challenge. You might be able to use some Mathematica for that. But let me nonetheless get started here, because I don't want to spend too long. I've already talked for 2 minutes, and I only want to put in about 30 minutes on this. So let's get busy here. Let's go ahead and open up Mathematica. Certainly you're going to go out to the cloud, grab your free version. I'm going to open up my paid version of Mathematica here. Mine has a couple of nicer features, but nonetheless, you should be able to do everything I'm going to do here on Mathematica. What do we want to start with? Let's call this unit tangent and unit principal unit normal vectors. Let's take a look at the unit tangent and what we know as the principal unit normal vectors. Remember, the unit tangent vector is a vector that's tangent to our curve, that points in the direction of our curve. And the principal unit normal vector is a vector that is orthogonal to that tangent vector, that unit tangent vector, that tangential direction. It points into the curve, right? It is 1 unit in length, right? It has all those properties. And let's see if we can illustrate that with some vector valued functions. Now keep in mind, how you input a vector valued function is you do let's do this to begin with here. Maybe the best way to visualize this maybe is to do a 2-dimensional demonstration here. You could certainly extend this up into 3 dimensions pretty easily, folks, with some plot changes. Maybe we'll get into that here. We'll see how much time we have. But let's start within the 2 dimensions. Let's call out a vector maybe like t comma t squared. Right? That's our pretty standard unit vector, or vector description here, right? A vector valued function. We might look at a quick little plot of that. Remember to plot these. It's a parametric plot. All right. We make a parametric plot of r of t over values of t. Maybe we look at values of t from negative to up to the value of 3. All right, let's get a little variety in there. No, we don't want to initialize any new cells. Just go ahead and run this. And we end up with this curve here. Let me actually resize. Let's do image size just so this is always fitting in here kind of nice. Do we really want to go small? And I got to spell image size correctly. All right. So that does kind of fit into our picture rather nicely here in Mathematica. Right? We may want to put some labels on our axes here. Certainly to label our axes, we've done all this before. It's axis label. And we might go ahead and label these axes x equal to x of t and y equal to y of t, respectively. All right, that'll put some nice labels on our axes. If we wanted to plot a point on this curve, certainly we could do a list plot, right? And maybe we plot r of 0. Gotta get 0 in there, not O, right? That would make a list plot. We don't quite see the list plot, and I got to be careful here how I put that in. I do think that has to go in parentheses like that, braces like that. And then let's call this plot 1, respectively. Let's make this our base plot, plot 0, the parametric plot. And maybe we rearrange those just in space. Right. And then let's show P0 with the base and P1 on top. We can't quite see this plot. Let's go ahead and make it a little bigger. This would be a plot style. And our point size. Let's call it out at point 0.02. Still too small. 2.5. If I go, let's just make sure it's showing up, first of all. There it is. It's certainly there. We just have to get it big enough. What if we go down to 1? A little smaller than that, right? So maybe go 0.7. Not 0.7, 0.07. Let's go smaller. There it is. Nice, 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 right? So that's where t is equal to 0 in our plot. All right. If we want to get some forward orientation, there's a couple of ways we could maybe illustrate that. I got this to work the other day. Let's see if this works. Certainly we can make a table of r at t values. For values of t, maybe starting at our -2 and going up to 3, and maybe we increment by 0.01 each time. All right. And let's call this table 1. You can see here I'm set delaying all these. We shouldn't run into any issue with that. And then let's do a graphics. So I'm going to call it G1. Because we're going to come down here and put it into our plot as a graphic of G1. All right. And actually, let me start this at 0 and go up to 2 in this. All right, and we'll see how that affects things. We're going to make a graphics, which is going to be an arrow, right? That's going to follow the values in T1. Oh, and it is there. It's a little hard to see, and that's due to our image size. Maybe we do want to make this a little bigger. Let's go 300. Right. What might also help our image here is maybe we do aspect ratio automatic and just see how it scales. It's already doing automatic. What does 1:1 give us? Okay, 1:1 kind of scales it into our space. If we put automatic in there, it automatically scales it accordingly. Here it's going to certainly, the scale of the x and y axis is off a little bit. So we get a nice image there. Right? And we can probably shrink down this point size now. We don't need it terribly that big. All right. But there is our arrow. It's kind of highlighting forward orientation. And I used a table to make that arrow. I think I used a Bezier curve before. We don't need to get that complex, folks. If I do want to change around some properties on the arrow, like for instance, I want to make it a little easier to see, make it a little thicker. I could write thick. It'll make it a little thicker. If I wanted to change its color, I could incorporate that into the group, right? And there is our, it's a little graphical analysis. Now, what we're going to want to do with this is we are going to want to, in a sense, look at finding our unit tangent and our unit normal vectors, folks. All right. So let's add that to our analysis here. And I'm going to do a little documentation to help us keep track of this. Let's look at unit tangent. Right. Let's find the unit tangent vector for r bar. Keep in mind we are going to need r bar prime of t, and we can certainly look at the derivative there. That is 1 over 2t. We're also going to need its magnitude. And remember how to get the magnitude of r bar of t. It is norm, right? We're going to need to take the norm of r bar prime of t. All right? And what we do note is when you take the norm, it is going to incorporate absolute values until you do I've done this in class with you folks, a full simplify on this statement, where in this full simplify wrapper, you're going to have to declare that t is an element of the reals. And remember, to get the element symbol following the t here is you're going to press the escape key, type in ELM, and then hit the escape again, and it'll turn to an element symbol. And then we're just going to type the reals. And now when I do that calculation, it eliminates that absolute value. Makes it a little cleaner for us. What are we going to do with that? Well, we can take r bar prime of t and divide it by that magnitude, right? And we are going to declare that as our unit tangent vector with respect to the parameter t. So I'm going to declare it as a vector here, folks. All right. The unit tangent vector, and you can see I use the function notation where I have my parameter t followed with an underscore. And it's all equal to this. It is equal to the first derivative of r, which is r prime of t, divided by its magnitude. All right. And when I hit enter, I should see that. And if I wanted actually to say that, maybe I could make a print statement. I could say print, right? Maybe we print unit tangent vector, right? And now it tells us ahead of time that that is our unit tangent vector, right? If we want to then follow this up with the principal unit normal vector, we might call this our u norm vector, right? It's also going to be a function of t, right? So we use that proper function notation to declare this. Let's actually have it state its value. And as we noted here, it is going to be the unit tangent vector, right? First derivative with respect to t divided by its magnitude. So that'd be a full simplify for what would be the norm of the unit tangent vector's first derivative with respect to t, where we again want to do a full simplify that treats t as an element of the reals. And you can see there we get that as our unit normal vector. Now, one of the things I might consider doing here is even wrapping that entire result with another simplify. You can see sometimes when you get these ugly results, Mathematica, you really got tired. Said, I'm done. But if you run a simplify on that, you can certainly get that to simplify a little nicer. So you can never simplify too much. When you have something complex, certainly, you can check that. Now, that is my unit normal vector, and maybe we print that. This print is going to be my principal unit normal vector, right? So now when I run that code, it does tell me what I have there. That is my principal unit normal vector. All right? And actually, let's highlight that here. Principal unit normal vector. And why get so anal here? But let's get that in there anyway, right? This is documentation. This is writing a code, folks. What we now have is a code that we can plug in any vector up here. Here I have t squared, but maybe I want t minus 2t squared, right, as my y of t value here, right? And certainly it finds its unit tangent and principal unit normal vectors respectively, right? Notice also, though, we get this graph down here. It plots it. itself, respectively. And it does plot itself over these bounds from -2 to 3. And in fact, we could make those variable. Maybe we make those bounds of a and b, right? So we can make this a bit more variable. And maybe we'll make that a -2. We'll make that b the value of 3, right? Still does those plots over those bounds from a to b, but we can change those up now. I can do from -4 to 1, and it does my plot from -4 to 1. Now, notice the arrow doesn't change around. To end up getting the arrow to change, remember the arrow's bounds were found here. We could do full bounds across that, right? We could do a to b this way, right? And it puts the arrow over our entire bounds. We could declare bounds for the arrow, right? Or maybe we consider putting it starting at 0. So I'm going to call out c equal to 0. I'm going to make that my lower bound here. And where else do I use 0 in all this? I think that's the only place. In our plot, our list plot. Let's go ahead and make this so we can actually highlight where that point is at too. Let's make that 0. And then let's make this go out to be -1. I don't know if we want to do so much that. Let's go c plus 1, which is going to point us in the forward direction there, folks. And we can certainly see that there. If we were to change around this a little nicer, maybe we go out to 4. Right, we can start to see that plot. All right. If I wanted to actually make an upper bound there on the arrow, maybe we do C. Maybe make our upper bound D if you really wanted to get into it, right? Maybe make our upper bound at 3. And then we can put an upper bound on our arrow here at D. You can have some control over that, right? And plotting out these values. We know that point is at 0, and this is our forward direction along that curve. And it acts a bit like a function. Here is the unit tangent. Here's that principal unit normal vector. Right? And I do all this to begin setting up the plots for the unit normal and unit tangent vectors. All right? Let's get a plot in there for the unit tangent vector. How I'm going to plot the unit tangent vector, let's see here. I think I can do it this way. Let's put it in to this grouping with the unit tangent. I am going to make a parametric plot, folks. The way I'm going to illustrate this vector is I'm going to write it as a line. It's going to be a line that's 1 unit in length. And I could make an arrow that's 1 unit in length, but I usually like making lines that are 1 unit in length. All right? So we're going to make a parametric plot. Right, of a line that is 1 unit in length. And how you make parametric plots of lines is you need to have a starting spot for that line. Now, where we're going to have this line start at is our value of r of c, right, or what we know as r is 0. Let's go ahead and have it start at wherever we put this point at on our graph, right? That is our control point we've set up here as 0, right? And let's have it go in the direction of, so we would add to that what we would say is the unit tangent vector at that value of c. All right? That's going to be a vector 1 unit in length. Right? That would be tangent to our curve at that value of c. We're going to add it on there, and then we're going to add on another parameter here. We're going to multiply this by some other parameter. Maybe we could do t. You know, it's going to be with respect to the parameter t, right? Where here we're going to consider t being across the bounds from 0 to 1. That's going to make it 1 unit in length. Right? Oh, what did I do there? I'm missing in brackets. Right there's my problem. I don't need the bracket in there. All right. Now there's my vector 1 unit in length. What I want to do is put that into the graph down here. So to put that in the graph, we're going to call this out as P3. right? That's plot 3, and we're going to come in here and layer this into our graph, P3. All right? So you can see it's right down in there. And actually, if we adjusted these bounds a little less, maybe we went from -1 up to just 2, right? And we had our arrow go from 0 to 2, right? We can see that unit tangent vector being sketched into our graph right there. Realize it's not quite into scale, all right? There's a little bit of a scaling issue. If you were to adjust your aspect ratio back to automatic, it's going to automatically scale your graph appropriately. I'll zoom in my window a little bit here. So that will be now a vector that's 1 unit in. See, that doesn't. Let's adjust our plot range here also. And these are other bounds we could certainly set in our program. Will full do it? No, we're going to actually have to take note here. Maybe we make these adjustable bounds. Let's go with adjustable bounds G and H, right, in our program. So G would be our lower bound in the range. So maybe we make it go no lower than -2. And H would be our upper bound in the range. Maybe we go no more than +2. Right? And then there we can see that 1 unit vector. Right? Notice the range is now set from -2 to 2. So I can adjust that in my program as I perform an analysis on these vectors. And notice that tangent behavior, right, at that location. If I want to get a little bit fancier here, I could actually come along and call this out as a certain color. Maybe we do a plot style. All right. Let's go directive. I like green. And maybe we make it a little thicker. All right, so it's a little easier to see in our graph, and right there it is. All right. That's the unit tangent vector at that point, plotted at that point. We could do something similar for our principal unit normal. Right? We can make a plot of it. We can make a unit. Oh, well, sorry. Let's make this right. This is going to be a parametric plot, another line in 2-dimensional space that is going to start at our point, r bar of C, and move in the direction of the unit normal vector at the value of C, and be 1 unit in length, where we're going to set that by setting our parameter T to only extend from 0 out to 1 unit in length. And if we overlay that into our plot, you can see there is our unit normal vector laid into place. Right? If I want to give that a particular color and style, I can go up and do a similar plot style on it. What did I just do there? Copy. Let's just bring this down. Let's put a comma in there. All right. So there is our unit tangent and our unit normal vector laid into this graph. And I could adjust my C value. We could go back to our fundamental case, right? A T squared, right? This is upper bound and lower bound in our graph. This is upper bound and lower bound on our arrow, right? Maybe we make this out to 3, right? Let's go from 0 to 2 with this. And then let's look at, again, G and H was our plot range. Anywhere from 0 out to 9 should be suitable, right? And we could even bring that down some if we wanted. Let's bring that down to 6. You get a little better picture there. If I wanted to adjust where C was at, instead of being from 0 to 2, maybe we go at 1 and have our arrow go out to 3, but this will certainly adjust where we're also looking at our unit tangent vectors and our principal unit normal. Those would be right there in our graph. And we could see those respectively. All right. If we wanted to, do I want to do this to you? This is already a really nice program. It allows you to plot out these points. Let's see here. Let's call this the base plot. These are our base plots there. All right. This is our... Right. Let's call this out a little different. Let's make that C. Is certainly where the lower and upper bound on our arrow would be. That indicates forward orientation, right? If we wanted to put J into these locations here, we can make this a little bit more variable. And make this a little bit more variable, right? A little bit more controllable. And maybe we want to look at that let's go 2. Right, we could certainly do that, and it disconnects itself now from the red graph. All right, we don't always have to be at that point, so that gets a little bit more fancy there with that. What we might say, these are right graph bounds. Right, these are arrow bounds. Right. What were G and H again? Oh, these were plot range bounds, right? And then this was, we'll just say, location of unit. Well, let's just call it out as T and N, right? Where it's going to plot those at in our graph. So you can certainly document that way and then have a bit more organization there, folks. All right. But that's looking at unit tangent and principal unit normal vectors. That is doing their calculations here. That is giving you some bit of control over a graphical analysis of these items, folks. We can see that happening down here. You could set this up for a 3-dimensional scenario. Would I want to do that here? Can I do that here? Let's copy and paste this over. What would be our changes? If I copied and pasted that over, let's add a dimension here. All right, I can't hit enter yet or I'm going to get a ton of errors. All right. A and B should be fine. C and D should be fine. G and H should be fine. J should be fine. This all should be... Here's my first issue. This is going to have to be a parametric plot 3D. But other than that, that should be fine. Oh, I'm getting a terrible amount of errors. Don't run anything yet. Then down here, this is going to need to be a parametric plot 3D. Right? And it's really all plot commands that change over here once you change your vector. This would be a parametric plot command 3D. This is a list. Is it list plot 3D? It is, I think, list plot 3D. Or is it list point plot? We're going to double check that here in a moment. Let me actually check that right now. There's list plot. It would make sense that it would be list plot 3D. We just have to adjust those settings. Generates a 3-dimensional point plot of a surface, right? So I knew it wasn't this. It's a list point plot. I thought it was. But that one always gets me because it would make sense. Intuitively, you would think it would be list plot. But here, this makes a scatter plot, a 3-dimensional scatter plot, folks. So it's list point plot is what we want to convert the list plot over to. So it's going to be list point plot 3D. Oh, and I hope I don't get any errors with this at the end. Our table is all should be fine. Oh, and then our last thing would be our graphics. Would have to go graphics 3D. All right, you would need to do some 3D graphics. Oh, and there we go. You run that code. All it was some plot adjustments. And you can certainly see there, folks, it runs just fine. All right. Changing over those plot commands and that one list plot, you can actually make this into a nice three-dimensional code also. And notice it does all the unit tangent and the unit normal vectors, right, for you really quite nicely. Right? So that is this code scene here, folks. Now, let me see. Can I get this nice in the screen? All of it in the screen? And then I will dip myself out for just a moment, and I will allow you to pause the video right now and grab that code and just see those changes if necessary. But they were all on the plot commands. Parametric plot 3D, parametric plot 3D, parametric plot 3D, list point plot 3D, and graphics 3D. Right? Those were all the changes. And then I redefined my curve in the three-dimensional context. All right there, folks. We're right at about 30 minutes. So, yeah, I don't think I want to go any further in this lecture video. This is the unit tangent and principal unit normal vectors in both 2 and 3-dimensional space. What I will do here is I will always make sure you save your documents. And in the end, I am going to publish this to the cloud. But I do think I'm going to do a second half to this where we're going to look at curvature. Right? We're going to look at curvature, maybe adding curvature to the imagery here. And the curvature calculation. And what else could we do? Tangential and normal components of acceleration calculations. I'll show you how to get through and put maybe a bit of a program together for all that here, folks. But I'm going to go ahead and just save this. Right? We're going to call this vector valued function programs for right now, because it's going to have a few things in it. Unit tangent, unit normal, it does that and does a little graphical analysis with all that for you. And then we will, I'll get, like I said, my plan is to do a curvature one that's going to build on top of this and look at that tangential and normal components of acceleration. Maybe we'll look at some velocity and acceleration built into this imagery. All right. All good stuff to look at here, folks, and I'll get some demo out to you on that very soon. But with that said, I think I'm going to end there. We're at a half hour, and I got to go eat some dinner. So that's where I'm going to go. It's 9:30 at night, and I haven't eaten dinner yet. So I'm going to go eat some dinner. And if you notice, it is later in the day, folks. I'm wearing what I had in class earlier, right? Just shooting this now. Wanting to make sure I try to get you something in some time where you can maybe make some use of it before the test as we go into it here. But